All right, so vector space properties of Rn. So in this section, we're going to learn about a subset and how to derive what a subset is to the actual vector space itself. So first off, what is Rn? So Rn is an arbitrary nth degree portion, so an nth dimension, if you want to call it. So we have two dimensions for R2, R3 is 3 dimensions, and we go on from there. Right, so nth n is, if you go on to think of it, is the nth dimension, which is kind of weird, right? But it's very, very theoretical. But so we just want to define what a vector is in Rn. And like I said, this is going to be the format going forward, how things are actually run when it comes to vectors, because there's going to be restrictions on each individual component of the vector itself. Okay? So the cool thing is a lot of this process is just theory or theorems based off what we already know, what we can do with vectors, going back to multivariable. So given three vectors, x, y, z, in Rn, and a and b are scalar vectors, that means all of this properties actually hold. So it's closed under the addition property and the multiplication property of scalar. Okay, given a scalar of 2, it holds under scalar multiplication, so we can multiply, flip it around. The best part is about vectors, right? They're about the same process itself. Same thing with just two vectors, right? The key thing is that they're still technically vectors or in matrices, so multiplication is going to be a little different of the vectors. But for now, we're just doing just straight scalar properties. And the other properties here of the addition and subtraction. So the nice thing is, this holds for addition, doesn't hold for subtraction. Probably for obvious reasons, right? This process doesn't work the other way. It's going to get a negative of it. Okay. The biggest ones going down here is these two here. Okay. So Rn contains a 0 vector 0 such that if I add 0 to any vector, I get the vector back. So that's what we call a 0 vector, which is the same thing as the addition rule, right? So 5 plus 0 is 5, so 0 is the 0 component of our number system. The next one is, given a vector, the vector negative x is its inverse or its opposite. I don't want to say inverse, but let's just say opposite for now. Is the opposite such that you get the 0 vector back. Again, right, it makes sense going back to just simply numbers, right? So negative 5 would be the opposite of 5. Okay. Now, these are all fun and dandy, but what we really care about the most is the next theorem. So a subset. What is a subset of these Rn's or these spaces themselves? So a subset W of Rn is called a subspace of Rn if and only if the following three conditions hold, meaning each of these have to hold to be a subset. If one fails, it's not a subset automatically. So the first one is that the 0 vector is in W. So where W is defined, I can calculate the 0 vector being within there. Okay. Second thing is, given two vectors of W, such x and y, therefore the addition is also in W. And then finally, given any scalar a, multiplying a by any vector in W is actually still in W. Okay. So again, very theoretical. So let's actually do a couple examples, see how this is actually going to work out. Okay. So let W be a subset of R3, defined to be this. Right. So we want to call, is this a subspace? Okay. All right. So again, how this format is done, and there has to be a little tweak here. So x1 and x3 are any real numbers. Let's just change a little fact there. Okay. So what does an actual vector look like in W? We'll just start there. So any vector x will be in the format, instead of x1, x2, x3, if I just replace it, is x1, instead of x2, it's going to be x1 minus x3 and x3. That's really what a vector represents, right? How this is actually defined to be. Okay. So we're just going to go down the list. So first one, the 0 vector 0 is in W. Okay. So what we're going to do is we're going to let x1 equal 0 and x3 equal 0. Okay. So if that's the case, what happens here? Well, this vector becomes 0, 0 for x1, x2, and we have 0 minus 0, which is just the 0 vector, which means it is in W. So it's a vector within this parameters. Okay. All right, so now let's go to number 2. So number 2 is the addition one. All right, so we're going to pick two arbitrary vectors. So the first one will be here. And we're going to add them. And I'll just use y's just for practice sake. Okay? So we have two arbitrary vectors that follow the same template, and we're going to add them together. So this becomes x1 plus y1. Adding this together. Okay. All right, so now I'm going to rearrange this a little bit. Okay, so I'm going to reach the middle part where the minus is in the middle. So I'm going to put this to this together. And put in parentheses. And then minus, since they're both negative, it's going to be x3 plus y3. Now I have that at the bottom. Okay, so now I'm going to define a couple things. I'm going to set let z1 equal the addition of x1 plus y1, and let z3 be x3 plus y3. And now if I rewrite this format using these new letters I defined, the top just becomes z1, bottom is z3. But now notice the middle becomes z1 minus z3, which is exactly the same format as our vector defined to be. So that means this addition is within W, or is contained in W. So the second condition actually holds. Okay? And now the third condition is multiplication. So let A be any scalar. Okay. So now I'm just going to multiply A by X. So that gives me AX1, and in parentheses I'll put this here, and AX3. Okay. Okay, so now I'm just going to distribute this. And now again, I'm going to just redefine my terms. So I'll be Z1 is equal to A times X1, and Z3 is equal to A times X3. So now this matrix, or this vector, becomes Z1 and Z3 in the bottom. And again, notice Z1 minus Z3, which is also still defined to be any vector in it. So it does contain in W, which means this is a subset of it. And that's how we have to do each one individually. Probably the most work is going to be the addition one because you have a little bit of manipulation itself. And you really didn't have to actually convert the letters if you didn't want to. You could have just said, well, this is just one value, which is the same here and here, which follows that exact template. And same thing here. This is this one is this one. This addition is here, here, and there. But it's probably easier to quickly just redefine it. That way it's easier to the eye to manipulate. Okay. So let's try some more practice using this new subset stuff. Okay. So let W and V be subsets in R3, defined to be this in each case. Now we've got a question, are these subspaces of R3? Which means we have to do the three conditions for each W and V. So we'll talk about W for now. So this is going to be the situation here. So we have vector 1, 2, 3 such that x2 is equal to 2 times x1, and x3 is equal to 3 times x1, and x1 is any arbitrary number I want. I forgot to put the brackets there, and here. Okay. Okay, so just like last time, I'm just going to rewrite what that means. Okay, so instead of x having 1, 2, and 3, I'm going to rewrite exactly what this represents. So it says x1 could be anything I want it to be. x2 is 2 times x1, and x3 is 3 times x1. So that's basically how my vector is. Okay. All right, so now let's just go down the list. Right? Okay, so let's say x1 equals 0. Well, if that's the case, that means x2 is going to be 2 times 0, and x3 will be 3 times 0, which means gives me the vector 0, 0, 0, which follows the same processes, so it's contained in W. Check. That works. Okay, step 2. Now vector addition. So again, picking two arbitrary vectors. Adding these together. Gives me that. Okay. So what I'm now going to do is factor out a couple things. So I'm going to factor out the 2 and the 3 respectively. And hopefully you notice it does actually work. So this time I'll let well, let's say z itself, z equal to x1 plus y1. Oh, I guess I have to call it z1 to use the proper way. So if I rewrite this, this now becomes z1, 2z1, 3z1, which follows the exact same template as a vector, which means it does contain scalar addition. And then the last thing, number 3, scalar multiplication. So again, let A be any scalar. So A times x would equal to that. Okay, and again, let z1 equal the multiplication of A times x1. So therefore I can rewrite this as z1, 2z1, and 3z1, which is in W. So this is a yes. That is a subspace of R3. Okay, so now let's try V. Okay. All right, so a vector V follows this template where it says x1, x2 or any number, and it restricts x3 to be 1. So literally is just that. Okay. Okay, so let's try the first one. I'm trying to figure out which one would actually work, but they actually didn't work. So let's try the first one. So let x1 equal x2, which is 0. So therefore, this vector becomes 0, 0, 1. Okay. So we have a problem because, remember, the 0 vector, it has to be this, which these are not the same, right? So they don't equal to each other, so no way. So therefore, it is not contained in W. So automatically, V is not a subspace because it doesn't do the first one. And in fact, it actually doesn't hold for any of the 3 conditions. So you can start with any of the 3 and it wouldn't work for any one of them. Ironically enough, there are some cases where it does hold for 1 or 2, but not actually all 3. So that's why we have to check every single condition to make sure it does actually work. Okay. All right, so now we got that. Let's do one more example. Now it's in R2, a little easier instead of R3. So given W is x1, x2, or x1 and 3 are any real numbers, is this a subspace of R2? Okay. So step 1, since they're any real number I want, so let them both equal 0. So therefore, a vector will be 0, 0, which is contained in W. So check, it holds the 0 vector. Number 2, add 2 of them together. Okay. And the same thing, I'll let C1 equal this addition, and Z2 equal the other addition. So it holds under vector addition, and then finally scalar multiplication. And same format. And believe it or not, we'll eventually talk about bases of a dimensions or bases of a field, and you'll see that this is actually more than just a subspace, is a basis for the actual vector field, which is pretty interesting stuff once we get closer there. But that's pretty much it. What this section is about is just defining what is a subspace, the steps to do so. Kind of like continuity is 3 major steps when it comes to it, and each one must be satisfied to work. So last one, that one holds, so this is yes, it is a subspace of it.